Cloud WAN Hub Comparison. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we are diving deep into one of the most strategically important networking services across the three major cloud platforms, the Managed Wide Area Network Hub. Every large enterprise eventually needs to connect dozens or hundreds of branch offices, data centers, VPCs, and VNets into a unified, globally routed fabric. Each cloud provider has built a managed service for exactly this purpose, and understanding how they compare is critical for architects working in multi-cloud or hybrid environments. Azure calls their service Virtual WAN, commonly written as vWAN. AWS calls their equivalent the Transit Gateway, or TGW. Google Cloud has built the Network Connectivity Center, abbreviated NCC. These three services solve the same fundamental problem from very different architectural philosophies, and those differences have real operational and cost implications that we will explore slide by slide. AWS Transit Gateway Core Architecture. AWS Transit Gateway is Amazon's answer to the same problem, but the architectural model is meaningfully different from Azure's approach. Where Azure Virtual WAN is inherently global, a single Virtual WAN resource can span all regions through its hub mesh, and AWS Transit Gateway is a regional resource. You create a transit gateway in a specific AWS region, and it becomes the hub for that region's VPCs and VPN connections. The core construct in TGW is the transit gateway itself, which acts as a regional cloud router. VPCs attach to the TGW through transit gateway attachments. Each attachment connects a VPC to the TGW routing fabric. Similarly, on-premises sites connect through VPN attachments or through AWS Direct Connect via a transit virtual interface, called a transit VIF. AWS also allows you to attach Direct Connect gateways to ATGW to centralize Direct Connect connectivity. The diagram for TGW shows a regional hub model. At the center sits the transit gateway. Spokes come in as VPC attachments. On the hybrid side, VPN and Direct Connect gateway attachments bring in branch and data center traffic. Routing inside TGW is controlled by transit gateway route tables, which you manage explicitly. This is a key difference from Azure Virtual WAN. TGW gives you full control over route table segmentation, allowing you to build sophisticated multi-tenant or multi-V or F designs where not all attached networks can reach each other. For multi-region designs, AWS uses transit gateway peering. You create explicit peering connections between TGWs in different regions. Unlike Azure's automatic inter-hub routing, AWS requires you to create the peering attachment, configure the static routes or route policies across the peering, and manage the inter-region transit yourself. This gives more control but requires significantly more operational effort at scale. Hub and spoke topology comparison. Now that we understand the core architecture of each service, let's compare how they implement the hub and spoke topology, the most common enterprise WAN design pattern. In Azure Virtual WAN, the hub is a fully managed regional construct. You do not configure routing protocols on it directly. Azure handles BGP peering with all gateway attachments automatically. The spoke VNets attach through hub virtual network connections, and the hub propagates routes between all spokes and all branches by default in the standard SKU. Route policies allow you to customize this default full mesh behavior and isolate spoke groups from each other. The hub can host multiple gateway resources simultaneously: a VPN gateway, an express route gateway, an Azure firewall or third-party NVA, and a point-to-site VPN gateway, all inside the single hub construct. In AWS TGW, the hub is also managed infrastructure, but the routing model is customer-controlled. The TGW has one or more route tables. Each VPC or VPN attachment is associated with a route table and can propagate routes into a route table. By default, TGW creates a single default route table. Enterprise designs typically use multiple route tables to implement traffic segmentation, for example, a production route table, a shared services route table, and a development route table where attachments in different tables cannot reach each other without explicit static routes. In Google Cloud Platform Network Connectivity Center, the hub is global and the routing model is based on spoke-to-spoke propagation mediated by the hub. Each spoke has a route propagation policy. The hub computes a merged routing table and distributes it to all spokes automatically. Google Cloud Platform uses BGP internally to manage this. Unlike AWS TGW, you cannot currently build multi-virtual routing and forwarding or segmented routing topologies natively within a single network connectivity center hub. All spokes in a hub share the same routing domain by default, though data groups introduced later provide some isolation. The diagram on this slide shows all three topologies side by side. Azure's Virtual WAN hub contains gateway services and automatically meshes spokes. AWS TGW sits as a regional hub with explicit route tables controlling spoke visibility. GCP NCC Hub federates spokes globally through Google's backbone. Routing and traffic management. Routing control is where the philosophical differences between the three platforms become most apparent. How much routing autonomy does each platform give you, and how does that affect complex enterprise designs? Azure Virtual WAN routing operates through a concept called routing intents and route policies combined with virtual hub routing. By default in the standard SKU, all spokes and branches connected to a hub exchange routes with each other full mesh within the hub. Route tables inside the hub allow you to control this. You can create custom route tables and associate connections with specific tables to build isolated routing domains. Azure also introduced routing intent, which allows you to declare that all private traffic or all internet traffic must be inspected by a security appliance, Azure Firewall, or a partner NBA before being forwarded. This simplifies insertion of security services into the routing path, which historically required complex custom routing configurations. AWS TGW routing is fundamentally table-driven and highly flexible. You define multiple TGW route tables. Each attachment is associated with one route table for inbound route resolution and can propagate its routes into one or more tables. This enables sophisticated designs. A shared services VPC that is reachable from all other VPCs but where production and development VPCs cannot reach each other. TGW also supports appliance mode, which ensures that traffic flows through a specific firewall VPC symmetrically. Both request and response traverse the same appliance, which is critical for stateful inspection. The TGW also supports multicast routing, which is unique among these three platforms. Google CP Network Connectivity Center routing is currently the most opinionated and least customizable of the three. The hub aggregates all spoke routes and distributes them to all other spokes. There is no equivalent of TGW's multi-table segmentation within a single network connectivity center hub today. Route filtering and import-export policies at the spoke level provide some control, and VPC-level firewall policies add security enforcement. But for complex segmented routing requirements, Google CP architects often supplement Network Connectivity Center with explicit VPC peering or shared VPC designs alongside Network Connectivity Center rather than relying on Network Connectivity Center alone. SD-WAN integration. Software-defined WAN integration is increasingly important as enterprises modernize their branch connectivity. Traditional MPLS circuits are expensive and slow to provision, and SD-WAN overlays have become the dominant enterprise branch architecture. How does each cloud platform integrate with SD-WAN vendors? Azure Virtual WAN has the deepest and most native SD-WAN integration of the three platforms. Microsoft created a concept called the Integrated NBA, where certified SD-WAN partners deploy their virtual appliance directly inside the Azure Virtual Hub, not in a separate VNet, but inside the hub itself. Partners with this integration include Barracuda Cloud General WAN, Versa Networks, VMware vCloud, and others. When a partner's NBA is deployed in the hub, branch offices that run the same vendor's physical or virtual SD-WAN edge device can establish tunnels directly to the hub-based NBA. The branch traffic then has direct access to all VNets and express route connected sites through the hub's routing fabric. Azure manages the lifecycle, scaling, and high availability of these integrated NBAs. AWS TGW integrates with SD-WAN vendors primarily through two patterns. The first and most common is the SD-WAN vendor deploying their cloud gateway or head-end appliance in a dedicated VPC called a transit VPC in older architectures, now superseded by TGW-based designs. The head-end VPC connects to TGW, and all SD-WAN branch traffic terminates at the head-end, then routes into the TGW fabric to reach VPCs. AWS also has the SD-WAN Attachment Partnership Program where vendors like Cisco Viptela, VMware vCloud, and Palo Alto Prisma SD-WAN have documented integration architectures with TGW. AWS Verified Access and AWS Cloud WAN also complement TGW for SD-WAN integration scenarios. Google CP Network Connectivity Center provides SD-WAN integration through the router appliance spoke type. A router appliance is a virtual machine running inside Google CP, typically a partner SD-WAN head-end or cloud gateway, that peers with cloud router using BGP. The NCC hub accepts this router appliance as a spoke, and routes learned from the appliance's BGP session are distributed to all other NCC spokes. Vendors with certified router appliance integrations include Cisco, Palo Alto Networks, Aruba, and Juniper. The advantage of this model is that the appliance runs in Google CP, so you get full access to Google CP's internal networking capabilities and can right-size the appliance virtual machine independently. Pricing model comparison. Pricing for managed WAN hub services is notoriously complex and often surprising. Each provider bills across multiple dimensions: the hub or gateway resource itself, data transfer through the hub, attachment fees, and VPN tunnel fees. Let's compare the general pricing model for each. Azure Virtual WAN pricing has two components at the hub level. First, the hub itself is billed at an hourly rate per hub, approximately $0.25 per hub per hour for a standard hub, which is $180 per hub per month. This is the infrastructure reservation cost. Second, and more importantly, Azure charges a data processing fee for all traffic that flows through the hub, currently $0.02 per gigabyte for traffic processed by the hub's routing engine. This data processing charge applies to VNet traffic, branch to VNet traffic, and inter-hub traffic. Gateway charges for the express route or VPN gateways deployed inside the hub are separate and scale with the scale units you provision. AWS TGW. Pricing is straightforward in structure but can accumulate quickly. There is an attachment fee of approximately $0.05 per hour per attachment each VPC or VPN connection attached to the TGW incurs this charge. At roughly $36 per attachment per month, an environment with 50 VPCs attached to ATGW is paying $1,800 per month in attachment fees alone before any data transfer charges. Data transfer through TGW is charged at $0.02 per gigabyte for traffic processed by the TGW. Peering attachments between TGWs in different regions also incur attachment fees plus inter-region data transfer charges, which can make multi-region TGW designs considerably more expensive than single-region designs. Google CP/NCC pricing is structured around data transfer rather than attachment fees. NCC does not charge a per-spoke attachment fee equivalent to TGW's per VPC attachment charge. Instead, you pay for the data transfer between spokes through the NCC hub, charged at rates that vary by the geographic combination of source and destination regions. VPN and interconnect data transfer charges apply separately on the hybrid connectivity side. For the site-to-site data transfer use case where NCC acts as a backbone between on-premises sites, Google charges a per gigabyte rate for the data transited across its backbone, which is typically competitive with MPLS providers for comparable bandwidth.